Here are my topics, watersheds and climate. And at the very end, if you need additional information, I give you the link to my personal webpage at CSU. I have two types. One is the classes with the erosion, sedimentation, river mechanics, where you can download the dearth of information from reports to PowerPoint to papers to spreadsheets, computer programs, and so forth. And the other one is really my research webpage that I've built up with graduate students over the past couple of decades. First topic here, watersheds and climate. The subtitle is your sediment source, sediment yield. I think it's very important. We have engineers and geomorphologists. Rivers don't carry just water. They carry a lot of sediment and also contaminants and so forth. And I want to talk about all those aspects here. Then we'll talk about dynamics, watershed modeling, flash floods, a little case study, and then climate change, my perspective about climate change. So really to get started here, we see in the western United States there, we have a lot of sediment. Typically, US Bureau works in western United States. Can get something order of 1,000 tons per square kilometer per year. And this is also in Southern America and the Andes, and you will see in Southeast Asia, that is where there's most of the sediment transport happening, Loess Plateau, especially in China, contributing a lot of sediment. And why is this? Well, because of deforestation, anthropogenic problems there, you get a lot of heavy rainfall from hurricanes, typhoons, some parts of the world that are going to tear down the hill slopes and bring all the sediment down into the reservoir. So therefore, we are concerned about this, about life expectancy of our reservoirs, and we want to see how long we can expect those reservoirs to last and how can we manage the sediment if we can, to reduce the amount of sediment and also extend the life expectancy of our reservoir. In terms of processes, then on the top right, you'll see a lot of splash and sheet erosion, which is, shallow millimeter thick water kind of draining on the surface where the splash is going to break particles, the cohesion between those clay particles. And then as the runoff takes place, then you form micro channels, rills. And if they get too big, they turn into gullies. And the difference between rills and gullies is depending on the size of the farming machinery. So the definition has been changing over the years. Initially, tractors were getting kind of small and little plows up there, but gullies got bigger and bigger as time went on. So gully erosion can be calculated more or less by the degradation you have inside the gully if they expand a lot. And typically, you'll find out that the amount of sediment coming from gully erosion, with some exceptions, are very small compared to the sheet and rill erosion. And for which, then we have a method that I have used over and over to calculate the mean annual sediment load on rivers based on the USLE. So the universal Solas equation is very simple. It has a factor R for the rainfall erosivity, so how much aggressivity or capability of the rain to detach and mobilize the sediment. It has a soil erodibility factor that does not vary all that much after all the K. And it has two geometric factors, L and S, and one for the slope length, L, and the slope steepness, S. There's a vegetation factor and a cropping management factor, C, and conservation practice, if you have terraces, if you have strip contouring and, things like that, that may reduce the erosion rate. This has been an old model dating back to 1965 with Wishmeyer and Smith, has been revised by them in 78 and remodified or revised by Ken Renard in the 90s, I think, and then it's been called the revised USLE, which is a bit more modern, which is very similar in structure to the old one. And this is a method that has been very robust, very helpful to predict the gross erosion rate on watershed. With this, then you can calculate. I have examples. I have a couple of case studies and examples throughout my presentations. You have an example here of a watershed in South Korea, about 1,300 square kilometers, and we can use GIS nowadays and 30-meter resolution, pretty standard here in the United States just as well. And then it's a pretty steep terrain, average of 40%, very steep terrain. And with GIS, of course, you can calculate all those parameters. So you have thousands and thousands of pixels, which you can describe the 6 parameters of the USLE, multiply them, and you're going to get a map of gross erosion. So that is the main idea here. We're going to get a map, multiply those factors from GIS studies, and I'll skip a lot of the details on how to calculate every single thing here, and I can refer you to papers if you want to know more about this. But essentially, the map is going to give you areas like in red where you get very high erosion rates in mountain areas, typically deforested, steep hill slopes. And of course, in the valley and the wet areas, then you're going to get very low. In blue, light blue, then you get very low erosion rates. And this is going to be a map to gross erosion that tells you where you can expect the erosion to take place and where you may mitigate and build little check dams or things like that, or reforest, or things like that, right? So that gives you the total. Then you average, you sum this up over the entire area, so you get something like, in this case, 4.7 million tons per year, and that is the mean annual or expected value of erosion that is going to be coming from the upland areas. Now you have your reservoir in Ettema Dam that I'll show more results about tomorrow. But at Ettema Dam, that you want to see how much will come into the reservoir, then you have to use the sediment delivery ratio, which is going to account for the fact that not all the erosion that's going to take place in the mountains is going to reach your reservoir. Some of it will be trapped into little ponds, trapped onto some floodplains, into wetlands, and so forth. So you're going to lose some sediment along the way. And typically, in this case, that's essentially a function of the drainage area. And about 5% of all that gross erosion is going to give you the sediment yield. And the yield is going to be the amount that's going to be, on average, entering your reservoir, right? So you get about 220,000 tons per year in that case. Specific degradation, some people I've seen, they call this a specific sediment yield, which is essentially the same thing. I use this from an old terminology, which I use in my textbook. So is you divide the yield by the drainage area, and that will tell you, in this case, about 160 tons per square kilometer per year. When I started this in the 70s, then Boyce went up to maybe 100 square kilometers, something like this. And I've been working on expanding and going beyond that, 1,000, 10,000 square kilometers. And here's an example. Those colored dots there are from a student, master student, Shukran Sahar, who did his PhD afterwards with Jeff Niemann at CSU in hydrology. But at the time, we did about a third of the country of Afghanistan, with this method to calculate. And we can measure, take the data on the sediment measurement, sediment yield in the river, and then calculate then the sediment delivery ratio. So this is how that sediment delivery ratio can be figured out. It's not just estimated from a graph there. You have at the river station, you measure sediment yield, sediment load, mean annual sediment load in a river, and you apply your model over the entire watershed, and the ratio of those two determines that sediment delivery ratio. And we find a range, anything around 1,000 square miles, 1,000 square kilometers, order of 5%, meaning 5% of all the erosion everywhere will make it to the outlet. Of course, your drainage area is smaller. Then if you get something like 1 square kilometer or so, then you get 50, 60%, the sediment is going to reach your outlet. At some point, we took all the data. Boubacar King did his PhD with me some years ago, and then 2007, so I guess 2005 or so, took all the data from all the reservoirs in the United States and look at specific degradation. We're looking at the tons of sediment entering reservoirs on a mean annual basis per square kilometer. And the key here is that, there are very few points over 2,000. So if you ask me, wherever in the US, then 2,000 would be kind of maximum that you will get for the sediment yield entering reservoirs. And of course, you can get a lot less depending on how much vegetation you have. You can get even 1 ton, so you get a very long life expectancy for just about any reservoir. But if I have a project, I don't know anything about it in the US here, and someone asks me, how many tons are you going to get? I say 1,000 tons per square kilometer per year. That's my basic number, my base number. And then from there, then I will look at it. It's very erodible. Then why not? Maybe I jag it up to 2,000. There's a lot of vegetation. It's very well protected. A lot of wetlands and a lot of, storage areas. Then I may go down to maybe 100 or something like that. So I get now a rule of thumb or a little number, a kind of target number I can start to play with. I have a, ballpark number I can work with. And here at on the right-hand side, you have the values that we just talked about from Shukran Sahar. He did his master's with me in 2013. So that's my first topic. It's kind of a static picture of the watershed and mean annual values. And this method I've used over and over, and I find it easy. Master's student can do this quickly. And if you're good with GIS, then you can figure it out, without taking a full class or something like that. So the second topic here, dynamic watershed modeling, is really for extreme events. We're looking at 100-year flood, PMP, PMF, things like that. So that is what I'm going to talk about now. I started this when I was a master's student. So looking 79 here on the left-hand side, we had a program called CalComp there, and I had 72 kilobytes to work with to discretize the watershed. Kilobyte. So I have here something about the size of a cigarette pack there. There's a 1 terabyte on it, right? I could not get the dynamic aspect, but just getting some mapping and getting started. And then we went at CSU from peaks and pokes to PCs, ATs, and XTs, and 286 and 286. Some of you may remember those days, maybe not the young folks here. The beginning of personal computers, and then we developed from there. So it's been a dream in making over decades. So at CSU, then we developed CAS2D in the 90s with Jerry, Baram Segafian, Fred Ogden, Bill Doe, Don May, you may know some of them, Darcy Molnar. The idea of getting some one pixel to the next, on the sketch there on the left-hand side, getting the rainfall on each pixel, get topography in 2D, transfer the water from one pixel, kind of cascade from one to the other, therefore the name cask in 2D. So that worked quite well for the water. Huh? And then we added the sediment. Little Billy Johnson at the Corps of Engineers in Vicksburg came and worked with us, and he developed something with the sediment there. Jeff Jorgensen took it on, they added some radar stuff. Hamid Sharma, Rosalia, they work on the sediment part of it. And then later on, then in around 2000, then we were tasked to look at an APA Superfund site in the Leadville, Colorado, called California Gulch. And we decided to adapt this to look for metals, heavy metals. So we're looking at, we got cadmium, nickel, and zinc, copper, and cadmium, and to look at contamination of, acid mine drainage there in that area. So therefore, we had to link this with environmental codes that would account for dissolved metals, adsorbed metals, and particulate metals. So we had to rewire this code that we had, our CAS2D, to accommodate that and link this together. And in doing that, we renamed this the T-REX for two-dimensional runoff, erosion, so it does water, sediment, and X for contaminant, and so forth. So what it does really, on a pixel basis there, we're going to get a rainfall. It's going to come into this. We use green and amp to calculate the infiltration. Very short time steps here. It's, order of a second or so. And then the excess water on the surface is going to run off and cascade into the channel. And then from the channel, so that's what we calculate on top. And then from here, then we have flow in the main channel, 1D. And then we allow the water to go onto the floodplains. We have a floodplain. The water can come out of the floodplain and then deposit there. The sediment can deposit there, and the water can come back into the channel afterwards. So this is the main structure of this code that is going to lead to something like this. So now we had some guys like Mark Ballou, John England, James Hallgren, Jehun, and Jazuri working on that. Mark would develop the code essentially with John. And then with Jazuri, we really tested with PMP, really maximum events, really large event to see how far can we go, right? So the idea is to calculate the surface runoff at the one-time step here. You can see in darker color, deeper water, surface water, it's really water depth that we calculate. You have the mountains up there where you drain, very steep hill slope. You have the city of Leadville, Colorado, right here. And then the water comes down here, and you have a little floodplain at the lower end. So it's running right now. So you dump a 3-hour rainstorm on this thing. The water's all over the place. And then the rain will cease at some point. The water starts to pile up in the channel. You infiltrate all water, runoff still from the city. Then water comes down the channel, goes onto the floodplain, and now then the water from the floodplain is going to infiltrate partly, and some of it will return to the main channel. So this is what the model does. It's kind of giving you a picture for extreme events. Some people would like to do this for continuous basis for 24/7 for 100 years, but it's not going to work very well. It's really for large events. So we can learn a number of things from that, from where the water comes from and things like that. And also for me, I learned something that, why does the flood stalls here, right? On the floodplain here, what's going on here, right? So you can see the water. If I show it again, I don't know, maybe comment on it at the same time. So see the water all over the place. It rains, and then you get different infiltration depending on vegetation and soil. You get a lot of runoff from the city, and then it comes down here. Okay, get high water here. The water goes onto the floodplain, and then will infiltrate gradually. But then things stall. It takes forever. Initially, it just rains so quickly, and all of a sudden, it's all there. And the water infiltrates or returns very gradually. So I learned something about the celerity of flood waves from this kind of model. You can see that if you have multiple watersheds side by side, they'll have a different response time, and this will affect the magnitude of floods coming farther downstream. Does it make sense? Yeah? So this is the kind of technology that we did. This video is really from James Hallgren, and it's already, I don't know, 10, 15 years old that he did for his PhD here. So here's a case study in South Korea, and there's some stream. Jay Hoon helped me with the graphics of it, but really the work was done with Mark Velu. He's at HDR Hydroqual. You can see how steep those hills are, typically forested, and you have large floodplains and whatnot. What we'll see here, this is a static picture. I'll show the movie in a sec. So you see that this little horseshoe bend is right here. So what we saw the picture is just this little square right there. Now you have the whole watershed area, okay? And so what we have, we display the water level from 0 to 10 meters. So in the main river, it can get pretty deep here at one instant. So you see the very little water left on the surface in the mountains. The water goes into the floodplains right here and in the main channel right there as you go down. The next one shows the sediment. So we can do the sediment with this and could eventually contaminate, but at this site, they were interested in sedimentation. Now you can see the water going onto the floodplain and getting some sedimentation onto the floodplain here. You see that? So this is a process that's very important to understand. And you'll see those mountains will drain very quickly here. And this will come in a little later in the hunt us, right? So now you can see the whole picture of the watershed and where things are and a bit dynamic view. So if this is running, no, let's see. Oh, yes, it does. So now we rain 100-year flood, three hours, if I remember. It's about 1,400 square kilometers. I'll show it twice. You can see initially this rains quickly, and this takes forever to drain out. So you can see how the prawns are going to be here. The sedimentation prawns will be here. You will see also on the floodplain. So you get water in the floodplain, you'll get some sedimentation also taking place there, right? It's not an exact model, but it gives you a good perspective on the dynamics of it. So does it work? You see the rain everywhere at the same time. This rains very quickly. This part is out. Then the next one comes here, stalls there, right? And this one here comes in later and eventually will come through. Does it make sense? Yeah. So you can see this kind of thing, water and sediment. How do we calibrate those models? Relatively simple in a way. We try to match the peak, if you get multiple peaks, and the concentration of sediment. So when we have data for, let's say, a 2-year flood or 5-year flood, we try to pick something big, and then we try to match those values there. And it's typically pretty straightforward. There's not much fine-tuning and a lot of calibration with this. And it's not an exact model either. Don't expect to know exactly the concentration of what time at every single pixel of this thing. But it gives you kind of a dynamic overview of your watershed and where the water comes from and at what time and which part may be coming, the flood may come before or after others, right? So So this is what this dynamic effect can do for you. Okay, a case study. We're going to go to Korea again, different student, different study. And I'll talk this afternoon about mud flows and debris flows, but this is one here where you cause a lot of damage, and it could have happened here, Colorado, California, I mean, Utah, you name it, right? The Western United States. There were big floods here, 1983, when I came here in the Wasatch Plateau and whatnot. So, I mean, we try to, what can we do with those cases? So this is an area close to DMZ demilitarized zone. So we had a little bit of a problem getting some data because we're too close to North Korea. But anyway, we untied all those knots there. It's a small area, 33 square kilometers, 12 kilometers long. We can get GIS. On top, you have elevation. On the right, the slope from GIS, essentially. Down below, left is the soil type. And then the right, you can get infiltration depth that you calculate over time. And then you're going to use algorithms to calculate the hill slope stability. So you can use some methods like SynMap, for instance. They have algorithms, and you need to understand the geotech, of course, the geometry, but you need to figure out how deep the soil is going to be saturated. And that is the key parameter there. So you can get some data like this, geotech. So that's more Coulomb stuff. I will not explain the details, but you get C plus sigma tangent phi. The angle of repose is here. And that is dry soil, and this is saturated soil, right? So as you become saturated, the friction angle will decrease by about 10 degrees or something like that, different samples. But the key point is this one here, it is the apparent cohesion, the C plus sigma tangent phi, and geotech here, the more Coulomb. Here you get about 16 to 18 kilopascal. But for dry soil, meaning you can sand on this, no problem. But as you go down to about 1 kPa, that's where things may start to slip away from you. The ground will unravel under your feet. Does it make sense? Yeah. So it is the area to watch out for. You want a number like my 1,000 tons per square kilometer per year, 1 kilopascal. 1 kilopascal of yield strength, of bonding strength is really a target number for me to look at for dangers of, landslides. Well, we can calculate those formulas I showed you before, that as function of you rain on the soil that is dry. So, I mean, your soil is stable because it is really unsaturated or dry soil. But now you saturate the layer, let's say 10 centimeter, the top layer there, right? So if you have 10 centimeter, you get that purple line, meaning that the factor of safety is above 1. So all slopes here, hill slopes, are stable. There's no problem. But as you get more water onto the soil, if you get 20 centimeter of saturated soil, now you get the blue line. So now you see the slopes are becoming unstable beyond 29 degrees. So as you increase the slope, your hill slope, at 29 degrees, it will be just at threshold. It may slip, may go. Make sense, yeah? And if you get more rain, right? So therefore we go towards PMP and so forth. Well, at 30 centimeter, 1 foot of depth saturated, soil, now you're going down to 25 degrees. You see that, yeah? So of course, then the big long rainstorm, one day, soaking rain there, and then you get a lot of infiltration in your ground. That's where you start getting problems, right? Okay, so you can apply this in GIS like we did. SynMap does something like this. Those dots are locations where landslide occurred there at that site. And the red zones are where, say, hey, this is not good. So what you learn from this, the hill slopes are unstable and the green is very stable. Make sense? Yeah. So, all right. So you get some people there where you tell them to go. Well, stay in the valley because, the hill slopes are not stable, isn't it? Yeah. If you look at the old photo after this event, look at this disaster. What happened here? You got some scars and landslides locally, but look at the valley. If you told the people to go stay in the valley there, those guys got wiped out. Here's the question for you. Where would you send the people? Where would you tell them to go? You told them not to go in the mountains because you get landslides. And if they stay in the valley, they'll get wiped out. where should they go, right? To answer this kind of question there, we look at the rainfall in blue. The color should be, I mean, blue is the rainfall on top. So, and the discharge at the bottom here. Very short, 3 hours, 6 inches of rain. So you get about 170 millimeters of rain in 3 hours. So you get pulse, you get flash floods, right? So, and we see this in the mountains here all over the place too. You remember the St. Rain here not too long ago, huh? So, and those precipitations are close to the record, at least short 100 minutes to 200 minutes, 3 hours. You're close to the 100, and you can get to the local PMP in blue, and in green you have the world greatest rainfall for a certain duration. So for us, when we analyze problems like this, then if you know the PMP, you go for that. If you don't, you can always go for the greatest that has ever been observed on Earth. You know, maybe in India somewhere, but you can dump this on your watershed and see what's going to happen. And you know it's going to be less than that. If it's stable for that kind of rain, it's going to be fine with less. Does it make sense? Yeah. So this is the kind of approach where you kind of you kind of narrow the area of, you know, parameters for the analysis. So here again, T-Rex I explained already. So we can apply this and do simulation on this thing. You're going to get water level here, and in green there low values, and then here you know floodplain, alluvial fan really, and you can get water levels that are much higher and so forth. So there you go. So you rain on this thing, short 3 hours. See the water from the hill slope goes into the channel. The flood comes into here in this area, and then eventually things will drain out from the upper areas. Now we know the maximum flow depth during this event, and we know the slope. So we can calculate the shear stress that comes out. And if you guys took my class years ago, 1 kilopascal is 1,000 millimeter. 1 pascal, 1 millimeter. You want to see at what shear stress you're going to mobilize some sand or gravel in a river. Well, 1 millimeter grain size needs 1 pascal as incipient shear stress to mobilize that. So 1,000 pascal is 1 meter. So now all of a sudden you can start mobilizing some boulders. Does that make sense? Yeah. So we can get a map of this here. You can see here in some areas in the lower area, you get 5 kilopascal. This thing can start to mobilize large, very large material. So here we can superpose this on maps, right? So forestry maps, and look at the size of the material that can go, right? So gravel here would be in blue, cobbles in green, large boulders in orange, and so forth. Does it make sense? Now you can see that is a potential. I mean, you may have only sand there. You can mobilize a boulder, but you have only sand, so you'll transport the sand, okay? But if you had a lot of gravel or so, and you can mobilize large boulders, well, the gravel is going to move out, that's for sure. I showed 3 pictures, called my student and sent him the field there, and he didn't get bombarded close to the MZ, but you can see the area. He went there. You can see the size of material that he went there in winter, long after the event, but the size of material that got mobilized, even the very upper part of the watershed here. So in the area where you get maximum shear stress, and you can see about 2 meter and a half boulder size, and cobbles really on the little alluvial fan. So this is the kind of utility for those models. You can calculate parameters. All right, very good. I want to give you my perspective on climate change. I'm not a climate scientist, but there are lots of lessons. I work with the geoscientists at CSU there for 25 years, and we call the Center for Geosciences. And lots of things I learned, but more or less with the civil engineering perspective here. So here's a little ghost picture. And I want you to watch this. It loops back on itself, and it's kind of interesting to see. I want you to notice, you see the map of the United States in the background, continental United States and Canada up above. And so what do you notice? So you can see in the upper part, when it's cold regions. So you see those clouds are all diffuse and very, very spread out and all over the place. Does it make sense? Yeah. So there's less variability in space and time. And you look in this area here, right? Like those clouds, they form, they go. Look at this, those cells. They pop, it's like boiling water, right? So you can see those cells, they form. Now suddenly you get thunderstorms, right? So then they move, and then the next one comes in, and so forth, right? Yeah. So climate change. What does climate change? What does it do? Global warming. What will it do? Well, you'll get more of what's in the south, those bubbles, and you get less of what's up north. Does it make sense? Yeah. So this is very important for us. The other thing is that as the atmospheres warm up, then the exchange, you see the big burst coming down from the north, right? It's like in Iowa, right? And then was it cold a couple of days ago out there? You get the burst down draft coming from far north there, right? So they get stronger over time. So therefore, with climate change, we'll get some warm air going to the Arctic, and we'll get cold air coming down our way. Yeah, you get stronger exchange, higher variability in temperature, precipitation, and so forth. Global warming, I mean, this is not new, right? So there's been a glaciation here. I grew up in Quebec, which is up here under about 5,000 feet of ice. And this pressed the ground down, right? And scraped all the floors and everything. And those ice caps have been melting for a long period of time, over 10,000 years. So in the Rockies, you can see in Alberta, the Athabasca Glacier Fields there, 1917, 2005, been melting for a long time. We can talk about accelerated warming. I think the trend has been there before, but it's not new. It's coming at a faster pace now. Here's my thought for you, that's in the Rockies, you see a level where above it you have snow and snow melt. It's about 7,500 feet. Yeah, there were studies on this kind of thing. I think it's around 7,500 feet. The floods are dominantly from snow melt, and below mostly from rainfall. But on top, if you have snow, what's going to happen? Snow is good in the sense that it may snow here today, it may snow there tomorrow, but the snow will stay there. Does that make sense? And when it will warm up, it will all melt at the same time. And this is a very stabilizing effect for vegetation. The vegetation, it's all at the same time of the year, and March, April, May, June, then vegetation starts growing all pretty much at the same time. But below, I call this integral in the sense that it is all over the place. Big area, think big surface areas that where the ice and the snow will melt more or less at the same time. And I look at the thunderstorms as being differential. You have calculus integral differential for engineers. Differential in the sense that it rains here today, but across the street there's no rain at all. The storm is gone. When it rains, it pours, and then it's gone. Does that make sense? Yeah. So there's a lot of spatial and temporal variability with the rain, and more so. So global warming is going to shift things up. Make sense? You get less of the integral and all uniform precipitation that's going to melt at the same time, and you get more of patchiness, a little bit here, a little bit there. You get a flood on St. Vrain, or no, you get the flood on the Big Thompson, or you get a flood in Fort Collins, and next year will be in Cheyenne, maybe, who knows, maybe Boulder one day, hopefully not. But, this is the differential, right? So kind of random and more or less more extreme. So for the snow part, here's a picture, 2008, Cedar Rapids, people from Iowa here. It's a relatively flat land, right? And then you got a lot of snowpack in winter, frozen soil, and now all of a sudden you get warm temperature, you get rain on top of this thing. The rain will help the snow to melt, and all of a sudden get large areas where everything melts at the same time. Does that make sense? Yeah? Integral, think big. You get major problems coming out of this thing, right? Look at train line, the roads, the whole city and whatnot. Do you have to build a flood wall around the city to protect the city? Does it make any sense? I don't know, but this is the kind of problem as engineers that we'll have to face, right? So here's another one from that area there. Wow, the train line here, they put some cars to make sure the pier does not go. Look, those houses, you get trees on the rooftop. I mean, I'm not talking about this site, but I'm talking this kind of problem where none of those structures has been designed for that condition. Does that make sense? Yeah. So those are extreme events that are going to impact us. I'm talking, this is the integral, the snow all over the place. And extended droughts is my second point here. And we have lived a lot of this in Western United States for a decade or two already. California, that's 2015. Every year it changed a little bit. This problem will reoccur again. The extended drought, those things that last for a long time and where those reservoirs are very low. And at the time I looked at this, I prepared this slide for the World Water Forum there years ago, 2016, I guess. But anyway, the government said, well, okay, we'll have restrictions of water. And I'm sure you guys, I probably would learn more from you than you'll learn from me about this kind of thing, water rights and what's going to happen in the West. And, all the wheeling and dealing with water rights and whatnot. But the problem partly is caused by climate change, partly with overallocation of water, irrigation, and demographic expansion. So it's a complex problem, and you guys are dealing with this. But in terms of climate change, there's another aspect here that we all live in Colorado, so I can go a little faster on that and have more time for questions, is the Colorado pine beetle that affected all our mountains. I'm talking a bit more like 10 years ago. And it really devastated our forest. It's not fall color as much as it is the pine forest has turned all red and create a lot of dry lumber ready to go. And at the first lightning strike, then you're going to get a forest fire that's going to come close to our living community. And that's 2012. It's already, 12 years ago. But and then, it takes 20 minutes to lose your life earnings that you put into your $1 million home or whatever. And just in a snap, then it's all gone, right? So this is a major problem. So linked to climate change in the Western from extended droughts. Heat island. This is less important, and maybe you'll never encounter that. But I included this because it does gain a little bit in popularity in terms of, people start talking about this. So what is this all about? I was in Kuala Lumpur years ago. Kuala Lumpur means muddy confluence. So in Malay. The city has been, developing quickly. And of course, they try to confine the river as much as possible because, you get those big skyscrapers to protect and the land value is very high. So let's get water out of here. Well, the problem is that with demographic expansion there, you're in a tropical area. So the monsoon, it rains about 180 days a year. They get 2,000 to 2,500 millimeters of rain every year. A lot of rain. So it's about 10, 20 times what we get here. So it's a lot of rain. The buildings and the people generate so much heat in the city that it is creating a heat going up. And then they get more precipitation, about 20-25% more precipitation in the city than anywhere else around it. Does that make sense? Yeah. And Kuala Lumpur, like I said, it's a muddy confluence. We don't see unfortunately, the river network around this thing, but it's the confluence of it's like a hand with 5 tributaries coming at the same place at KL. And now you get flash floods, and they all come more or less at the same time. You remember my little video earlier? We didn't take a video of this one, but anyway, you would see that all the floods coming at the same time. So what they decided to do, well, for one, the problem is that of course you get a lot of water in the city. You get happy campers, like we call them, right? So, and they have 50 million ringgits. That's about 3 ringgit to dollar. So I would say about $15 million a year of damage there in the city there. And, let alone the problems that go with flooding here. Their solution there has been to build a tunnel and get the water here under the city and get this on the other end, right? So the tunnel will pass some cars. So they use this for cars all the time in both directions, 2 levels. And then when the flood comes in, you have 20 minutes to close this thing, get the traffic out, all the cars out of this place, and they get the water through this tunnel. And they get to evacuate those floods through this tunnel. And then after the flood, they come with power wash cars, clean up the tunnel and they resumed the traffic. So they solved the traffic and the flooding at the same time, or a combination of this. It's an expensive solution, isn't it? So this is a machine to bore that tunnel. I mean, this is just a monster thing, right? I don't remember the cost of this thing, but it was in the billions of ringgit. So probably, I guess, don't quote me, $3 billion US dollars, something like that. Sea level rise and temperature. This is data from Patrick O'Brien, who did PG with me from the Corps of Engineers. We worked with San Francisco district for a while and whatnot. So this water level in San Francisco, from 1850 or 55 all the way up to 2015 or so, you can see a steady rise in water level. It's not that much, but 30 centimeter there over 100 years. So it's going up, it's creeping up, it's creeping up. So you can look in the US, get a map here, right? So, well, you see all continental United States there, up, the water level going up all the way up to Newfoundland, really. Farther north, if you look at Alaska, because of all the glaciers, all the weight that was pushing down the ground there, right? Now the ice is gone, so the land is going up, relatively speaking, right? So the subsidence really is in this lower area. The worst is New Orleans, right? Combination of, it's a delta, right? So you consolidation of the sediment. You get oil and gas also going there. So it's about 10 millimeters, if I remember, 10, 12 millimeters a year. Yeah, so 1 centimeter a year, so every year. Yeah, so this is, a problem, right? So you may remember this, 2012 again, LaGuardia, New Jersey, right? So normally tide should be within those two lines, right? But they got the surge from a hurricane that was, or probably a tropical storm that was, offshore, but still influenced the tides. And then you start flooding the airport, then you get a major problem. Sea surface temperature. This is a biggie here. Now you'll understand why in a minute. You see, from the west coast of Africa, they're all the way to Florida. This is where the hurricanes form, right? So if you get global warming, change in sea surface temperature, 2 to 3 degrees Fahrenheit, okay? Over 100 years, I think this is. It means that warmer oceans mean stronger hurricanes. So what used to be a category 3 hurricane may now be a category 4. Yeah, what was a 4 will be a 5. And, it's very hard to separate whether it's due to climate change or not, right? But it means that, we'll have to face some biggies. This is Katrina, when it was category 5, shortly before it hit New Orleans, so 2005. So category 5, see the eye of this thing about 35 miles in diameter. And you see on the western side, you have Texas, maybe, I'm not sure if you get Galveston. You get New Orleans, Lake Pontchartrain, and then you get Mobile, Alabama, Pensacola, and you have, you see the size of this thing, just huge. You can get a lot of rain over large areas. As much as I talk about the integral for the snowmelt, you get a bit the same effect right here, where you get a lot of rain for a long period of time. Yeah, and it will get stronger because of climate change, sea surface warming. Yeah, so New Orleans, 2005, $108 billion. I know we don't like to pay taxes. Nobody does, isn't it? But I mean, what do you do? I mean, look at all those houses underwater. It's just a major, major, major problem. What can we do? I'm about near the end of my talk here. What can we do about this thing? Well, in that case, they like boring. They build a surge barrier there. $1 billion. It's 1% of the cost of the damage from Hurricane Katrina. And you look at this thing, wow, those surge barriers are there. I mean, this extends miles and miles, but it's not very high. There'll be another category 5 going through this. It's going to flood this over. You probably need a wall that's probably 28, 30 feet high to prevent category 4, category 5. You think people want to see a wall in Mobile, Alabama, all the way across there, that's 40 feet high, the height of this room, maybe 2-story? They say, those engineers, they're nuts, isn't it? Yeah, but this is the kind of force that we're talking about and the cost that goes with it. Here's another problem that may affect people working more on the eastern side of the United States there. See, the hurricanes, like I said, start from Africa and come up here, right? Then some will circle around there, some will go hit Florida, some will go through New Orleans, some will go through Texas. But here you get category 5, huh? So H5, and it was down to 3 by the time it hit New Orleans, right? So, but it goes on and on. It's still a tropical depression all the way up to Nashville and so forth. So you can see what we thought before would hit mostly the coastline and then no problem, right? But it's going inland farther than we expected before, right? So as a result of this, then you get problems like Nick Koutsounis was working for the Corps, did a master's with me looking at the Bluestone Dam in West Virginia. And the original design, 1938, was 430,000 CFS. And they updated this. And now they're at 1.5 million. That's 3 times the original design. So you have to adapt your structure for much higher discharges there, right? What are you going to do? Are you going to store this water or, so a lot of engineering work ahead of us. And that is going to challenge us and our children, I think, for quite some time. Other things that can be done, the Corps has been working on. This is a picture from Coastal. Kate White there, she's, I think, in charge of all the environmental effects there for the US now. She was at CREL for a while, worked a bit with her and Patrick O'Brien, but like levees and storm surges, mostly coastal stuff. But the Corps is really actively concerned about this and working on various aspects of this. And for us and the population is I don't know, we have too big, get a polarization there, like we see in politics a little bit, but what are we going to pass on to our next generation, to our kids and whatnot, right? So they say we're not reacting fast enough, right? So, Greta Thunberg, for instance, we need to do something right now, stop oil and gas, and, it's very drastic and whatnot, but still, it's a concern for them. Can we go snorkeling and see all those beautiful corals there in the tropics and whatnot 20 years from now? If you get change in temperature of 2-3 degrees, and I don't know, right? So she had the microplastics all over the place around the world. I heard they are now even in those water bottles. I mean, it's kind of scary enough, isn't it? And we have the other side of the coin there, where people will say, well, is this true? Is this real? I would bet you have polled the people in Iowa on Monday this week, say, you believe in global warming, and then it's 40 below outside, and oh no, we need warmer temperature. Let's pump oil and gas and whatnot. You know what I mean? So yeah, there's something about hydrology that you can send a warning to people and say, you're going to get a flood there. With all technology, you're very high risk of getting flood in your house there in 3 hours from now. Get out of there, go somewhere else. People will say, no, I stay in my house because that's where I feel safe, and you may be 100% right. It happened in Germany, actually. It was a flood out there, and they issued flood warnings and everything, but the people did not want to leave their home. It never happened in their lifetime. Therefore, they don't believe what you're going to tell them, and they are going to stay in their house anyway because they feel safe. There's something with communities that we have some work to do, and it's not just a scientific problem, it's a really communicating our ideas and what we're doing, and because we're working for the people there, right? We can get some mapping of problem source areas in sedimentation. T-REX, we can simulate extreme events. Our models for flash flood, you can get some parameters like erosion. Climate change, widespread flooding from snowmelt, large areas, right? So, and extreme localized thunderstorms, from as a result of climate change, global warming. My presentation is a result of lots of people, especially PhD students there, from, Jerry, Barham, Fred Ogden, Bill Doe, Don May, Darcy, and so forth, right? So Mark Ballou and John England and James Hallgren, beautiful video, some Koreans and some people at UITM in Malaysia, and Patrick and others from the course.